Welcome everyone. So this is the first topic for our next unit, organic chemistry, and we'll be looking today or now at alkanes. We'll look at its structure, slightly touch on its reactivity, and primarily spend some time on naming and talking about isomers. So feel free at any point to pause, especially in a couple of slides. It would help if you write some of the rules of the nomenclature of alkanes down. Now I won't silently wait for it for you to possibly finish, so I just suggest then to press pause and continue when you're ready. So to begin, organic chemistry is, I'd say, relatively new, given that in the early 1800s there was what was still thought of as a vital force, so nothing that was organic or living could be synthesized because there was a vital force that had to exist. And this was started to be contested by chemists in the early 1800s who was able to synthesize a known organic substance that is found in urine, urea. So that vital force idea kind of started to go out the window then, and we'll talk about distinguishing at first what is organic and inorganic. So something that is organic will have carbon and hydrogen. There are some exceptions, primarily these. Carbon monoxide is not organic, neither is carbon dioxide, and hydrogen cyanide. Other than that, anything that usually has carbon is going to be considered organic. And we talk about carbon at first because carbon is unique. It has a specific Lewis structure, and you can take the time now to just review what the Lewis structure for carbon would be. Maybe I'll go ahead and try to draw that Lewis structure for you without or either actually just with a mouse and not any other fancy device. So we'll see how it looks. But the carbon Lewis structure, again, only the valence electrons. We have 4 valence electrons. Number of valence electrons, we have 4. The electronegativity value for carbon, I believe it's 2.55. And bond hybridization that happens to create these 4 bonds is that's actually not a bad S, sp3 from our previous unit. So these 4 bonds created by this sp3 hybridization, a relatively strong bond, allows for carbon to be involved in different types of bond formations with different sorts of elements. So we'll get now into talking specifically about hydrocarbons and how to name them and what they look like. First, we'll learn how to draw them. We'll look at the basic sorts or the basic types of saturated chains. So a hydrocarbon, given its name, is anything that has or that is composed of carbon and hydrogen only. And today we'll only look at saturated hydrocarbons, which means all 4 bonds of carbon exist as sigma bonds, either bound to carbon or hydrogen. Now it helps, of course, if you see examples of these, but before we do that, this is just a mnemonic device that I recall learning. It's monkeys eat peeled bananas, where the first 4 hydrocarbons have the same letter as the beginning, as the first letter of each word in this phrase. So M would be methane, E is ethane, P is propane, and B would be butane. You'll see these substances now, and here they are. So they're given to you in their structural forms, the formula as well, and if it helps, you have a 3D structure, ball and stick figure here. So methane right here has 1 carbon, 4 hydrogens. Ethane has 1 extra carbon, and 4 of its bonds are filled, 1 with a carbon-carbon bond and the other 3 with hydrogen bonds. This just repeats. Propane has an extra carbon, has an extra set of hydrogens. Butane, extra carbons, so now there's 4, and 10 hydrogens. Chains can get quite long. They go well past decane, and we'll actually for our class we'll stop at decane. We won't go past 11 or 12. And if I do, then I'll be sure to give you the parent name, and you can treat it as you would normally treat the names as we name, if that makes sense. So what is taking a look at the molecular formulas? Try to come up with, and if you need to pause, go ahead, but think about what pattern you see between carbon and hydrogen. Now, given a certain number of carbons, let's say n, so n number of carbons gives us how many hydrogens. There's a general formula that we can come up with where if we have a certain number of carbons, we can immediately figure out how many hydrogens there would be in a saturated hydrocarbon. So go ahead, take a moment, think about that, and you can pause again if you'd like. So if you've paused or unpaused, or you just wanted to continue, this is the formula. So for every n carbon, you get 2n plus 2 hydrogens. Now, if you go back to the previous chart, you'll see that for every 6 carbons, if you plug in the formula, we should expect to have 14 hydrogens. And in fact, we do. 2 times 6 is 12, plus 2 will give us 14. So that formula, this relationship here, this linear relationship holds true. Now, we draw alkanes, so the saturated hydrocarbons, in the structural forms. They, of course, actually don't exist this way. They look more like what you see at the bottom here. Now, this can be drawn as a stick figure, and solely a stick figure, where each of the vertices, so the ends and the pointy parts here, they are all carbons. And it's assumed then that that these carbons are saturated by carbon-carbon interactions, but primarily by hydrogen bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, and they're for octane, so 8 carbon atoms, and we have 8, I should have 8 vertices, 1, 2, 3, 4, 5, 6, 7, 8. So this depiction, this drawing of carbon in its stick form is represented by this more complex form as well, and vice versa. So we're going to simplify things by drawing them as stick figures, but know that they can also be drawn as you've seen them before. So let's try doing that now. I'm going to see if I can take out a pen here. Black is fine. All right, so we have 1, 2, 3, 4, 5, 6, 7. We have 7 carbons in total. I'm going to try to draw this as a stick form, again with my mouse, so we'll see how this goes. So stick, 1 is there, looks like that's over there, and we have that. And on the 1, 2, third carbon, 1, 2, 3, we have 1 carbon, 2 carbons. So this structure, this entire structure here is represented by this stick figure. Okay, now carbons don't necessarily have to exist as long chains. They can curl into themselves and become cyclic, also called a cycloalkane. So in order to name these, all we do is we add the word cyclo as a prefix to the beginning of the parent alkane name. So this 3 carbon 1, 2, 3 propane from monkeys eat peeled bananas is now cyclopropane. And whereas this would have been simply butane if you were linear, now as a cyclic form is cyclobutane, and so on. So that cyclo prefix is simply added to show that it is cyclic. And this can also be drawn in stick form. Okay, let's do that. So we're going to draw 3 diagrams here. Let's see if I can use lines instead. No, I can't. Alright, so we're going to draw a cyclopropane, so 3 carbons will look like a triangle. That looks a lot better than my previous drawing, triangle. 4 carbons, so a cyclobutane will be drawn like that. And a 5 cyclopentane, kind of like a house picture. Okay, a little better than that, but you get the idea. Go back, select. Right, so here are our formulas. So we have 1, 2, 3 carbons, and off this carbon we have 2 hydrogens, we have another 2 hydrogens here, and another 2 hydrogens here. So the formula would be, let's get a pen, formula would be C3H6. And the cyclobutane would have 8 hydrogens in total, so 4 carbons and 8 hydrogens. So let's just stop there, but you can do the same thing for cyclobutane, and we can come up with a formula then, a relationship between the number of carbons and the number of hydrogens as we did before with linear alkanes. So if you'd like to stop or pause, I should say pause here, to take a second to figure out what that relationship is, would be a good exercise. So this relationship is where we have n number of carbons. This one's possibly a bit easier to figure out. We would then have 2n hydrogens. So we don't have that plus 2 as we did with the linear alkanes. We can now talk about structural isomers where we have a compound that has the same formula but might have a different structure. So there are 3 here. We show 3 different isomers of pentane. So this has 5 carbons, 1, 2, 3, 4, 5, and we see that it has the same formula for all 3 structures here, but they are noticeably different. And we'll see as we practice naming, and you can go back to name these isomers, they have very different names and therefore are different compounds with different properties. So same formulas, 1, 2, 3, 4, 5. That would be 12 carbons, so C5H12, but very different names and structures and properties as well. So these are structural isomers. Okay, now to the interesting stuff. So hydrocarbons, we're going to just define how it looks. So a long hydrocarbon chain, such as this, can have portions or hydrocarbons attached to it, so smaller ones. The larger chain, though, is called your hydrocarbon backbone. Now, anything that comes off of this backbone that is also a hydrocarbon is called an alkyl group. And today we're only going to look at alkyl groups. And following this, we'll look at different types of substituent groups, but we'll get to that later, like I said. For now, it's just this is your hydrocarbon backbone, and if there are smaller chains or smaller hydrocarbon chains attached to any of these carbons, well, I suspect it would have to be just these 3. We'll get to why later, but if there's anything branching off of it, that's an alkyl group. So, what is an alkyl group? So we have a couple pictures here of 2 different hydrocarbons, 2 different saturated hydrocarbons. So I'm just going to follow instructions here and circle the alkyl group. So this is the parent backbone. So notice the longest chain, 1, 2, 3, 4. This would be the alkyl group. And here, 1, 2, 3, 4, 5. So now a 5 parent backbone. This is the alkyl group, this whole piece over here, including this carbon off to the side. Now, a question that might come up, you might think, well, couldn't you have said that this is the backbone 1, 2, 3, 4? And it's definitely true. You could have said that this here is the backbone, in which case this would have been the alkyl group. But either way, it would be named the same. And we'll get to naming later, but just for now, recognize that you have longest chain is your parent backbone, and any hydrocarbon that sticks off of it is an alkyl group. Okay, I'm going to go through briefly just the first 3 rules. The next 2 that follow this, we will look at through examples. So there are 5 steps to name, or 5 things to consider when we're naming alkanes. Now that's not all of them. That's not everything. There's probably well more than 5. Now what will follow these 5 steps right now? Like right now you only see 3, but there are 2 more in the next slide. Are examples, and those examples will help us better understand how to name alkanes. And we'll go back to these rules as we need. So first, the first thing you should always do is try to locate the longest carbon chain or the parent chain. Then try to identify any of the substituents or the alkyl groups that are attached off of that longer parent chain. Best thing to do, so step 3, is to number the parent chain from the end that will give you the lowest possible carbon number. Now this part may not make sense right now, but when we get to examples, some examples, they will. So this is an important point, and I've started this here. If there are 2 or more groups and the numbering is tie, the group that comes first alphabetically gets the lowest number. There are many different types of, or many different situations that can arise, and that's just an important point to note and to refer back to when we're naming. So these last couple of rules are for special situations, and we will get to them, so I won't talk too much about them, but I can briefly say that if there are more than one, there's more than one alkyl group, so there's 2 of the same type of group, or 2 of the same type of hydrocarbon attached, then you would use the word di, as or the prefix di. If it's more than that, so there's 3 of the same, it would be tri. If there's 4 of the same, it would be tetra, and so on. Again, we'll get to examples. Now, the last portion here, the rule 5, is basically outlining how to name complex substituents. So that's when the branches have branches. Now, you won't get many of those, but we will go over one example today. One more thing that might be important to say is that just in general, and that's just this part over here, separate words. So words are separated by hyphens, and we separate numbers by commas. Also, there might be many different ways, or at least a few different ways to name some larger hydrocarbons with different substituents and alkyl groups, but always go for the simplest possible arrangement. You might be able to name something using a complex method, or using this complex set of rules for complex branches, but if you don't have to, if there's a simple way of doing it, then that's the correct way. So simplest is best, because it can get complicated when it doesn't have to. But first, I've mentioned alkyl groups, and I did say alkyl groups are any branch that comes off of the parent backbone that is also a hydrocarbon. So the parent name, so methane, if we have one carbon with its three hydrogens attached to a parent chain, then instead of it being called methane, if it's a branch, so if this is branching off of a carbon backbone, it's called methyl. Same goes for ethyl, propyl, isopropyl, butyl. So these are very common alkyl names. So the general rule here is take the root word of your alkane and add the suffix yl or il. We'll get to examples. So this is a pretty simple one. Here we don't have any branches. All we have are 1, 2, 3, 4 carbons. It's fully saturated. So 4, if you remember monkeys eat peeled bananas, the banana would be butane because there are 4 carbons. So the name here is, maybe I should write this down. The name is butane. Okay. Now, in example A, we have a parent backbone, obviously longer chain here, 1, 2, 3, 4, 5, 6. Now, when I've just named them, 1, 2, 3, 4, 5, 6, and I started off to the left, but I could have started off here to the right. So let's just try doing that again. 1, 2, 3, and off the third carbon, we see that there's a branch. Now, third carbon branch. If we started naming on the other side, we'd have this carbon being 1, this next one being 2, 3, and 4. So we have 2 options here. We could say 3 and a branch, or we could say 4 and a branch, but we always go with the lowest number. So the name for this is going to be, at least the parent is 1, 2, 3, 4, 5, 6. That's hexane. And off of the third carbon, we have 2 carbons, or 2 carbon branch, which is monkeys eat. That means it's ethyl. We have to change the N to YL. So off the third carbon we have, I should change that to select. So off the third carbon we have ethyl that exists on the parent chain off the third carbon called hexane. Right? Not too difficult. Another similar example, we're going to start naming on the left, or numbering I should say, off the left hand side, because that's going to give us carbon 2. So we have 1, 2, 3, 4, 5, 6. So it's hexane again, but this time it exists, this branch exists off the second carbon. So it'll be 2, and this alkyl group is methyl. Since there's only one carbon, it's then 2-methyl hexane. Feel free to pause anytime you want, wrap your head around this. It does take some time to process this, and of course to copy down these structures. So whenever you'd like, you can pause. But we're going to move on now. Okay, I took the liberty here of highlighting the parent chain. It's just the longest chain. So here we have an example where we have long chain. It doesn't necessarily have to go left to right. The longest chain, and we have substituents or alkyl groups. So here's one, here's another one, here's another one. They are all the same, so they're all methyl. We have 3 methyl groups attached to different carbons. Let's start naming, or rather numbering. So off this carbon we have 2. So starting at this carbon, we then have at the second one a methyl group. Third, at the fourth one we have another methyl group. And at the fifth one we have another methyl group. So 2, 4, 5. There are 3 methyls there. Now let's just remember those numbers. So 2, 2, 4, 5. If we named or if we numbered the opposite end, starting at the opposite end, we would have 1, 2, 3. So 3, 4, 6. So 3, 4, 6, compare that to 2, 4, 5. The name is going to be 2, 4, 5. Since those are lower numbers, we should choose the simplest and lowest number. So 2, 4, 5. And this time, though, we have to add the prefix tri. Now tri, because we have 3 methyls. So we say 2, 4, 5. And at those locations, we have 3 methyls, and the parent chain is heptane because there are 7 carbons. 1, 2, 3, 4, 5, 6, 7. So it's 2, 4, 5, trimethyl heptane, and since we are separating numbers and words, we use a hyphen, and whenever we're separating numbers, we use commas. So that was that last rule there a few slides back. Okay, so this is a different example. Here we have again, another heptane parent backbone. We also have 2 methyl groups attached. Here, 2 of them are at the third carbon, and we also have another branch, but it's not, unlike the previous example, it's not a third methyl, it's a 1, 2, it's an ethyl. So we're going to see what we do for naming this, because it all has to come together a certain way. So ethyl, this longer branch off of the main chain, has 2 carbons, but what's important in this case is ethyl E comes before M, so we have to list these substituents, these alkyl groups, alphabetically. So ethyl is going to come first, and the methyls will then come second. Okay, now because there are 2, we also have to add a prefix to methyl, so it'll be dimethyl. But that prefix is separate from the real name. So that's where it can get a bit confusing, because you might think D comes before E, so we should actually put dimethyl first, but that isn't the case. Ethyl comes first. I'm going to just reveal the name here. So on the 4th carbon of the parent backbone, we have ethyl. Off of the 3rd carbon, we have 2 methyls. Now, take note of this. 3, 3 dimethyl. Off the 3rd carbon, we have 2 methyl groups, so we have to write 3, 3. Account for each one by repeating the same number, so 3, 3. We add the prefix di, but we're still citing alphabetically based on their original name. So ethyl comes first, then methyl. And then, of course, we end off with the parent name, heptane. Our next example that I used to have, I think this might be your last one, I used to have hidden here, then I thought, no, I wanna show you how complex these complex ones can get. And I want to also help you out by giving you the name first so that we can make reference to it. I've taken the liberty of highlighting in yellow the 13, that's tridecane, so the 13 carbon parent backbone there highlighted in yellow. Now this is a complex branch, or this is a complex alkane, because here we have, off of the 7th carbon, we have a branch. but the branch has branches. So that's what makes it complex. Off the fifth carbon, we have a simple, regular ethyl group, so that's nothing to worry too much about. It's this complex branch that gives us kind of a bit more work. So let's start naming this. I should change something here. Okay, let's just start naming this. Off the seventh carbon, we have a branch, and the long branch is this 5-carbon long branch. Off of that branch, we have a methyl off of the first carbon and another methyl group off of that second carbon. And I'm going to go ahead and change change this is not alphabetized under D. So we're going to change this around just to make sure that this is correct. So off of the first carbon we have a methyl, off the second carbon we have another methyl, so that'll be dimethylpentyl. Now we have to say that this dimethylpentyl complex group is attached to the 13 carbon chain backbone off the 7th carbon. So off the 5th carbon, you can ignore the name, there has to be, again I have to make a slight adjustment here, but off the 5th carbon we have a simple ethyl group. Now, what's wrong with this name, actually, maybe it's good that I made this mistake because you can take a look at what can happen very, very easily, especially if you get more and more complex branches. So I'm not going to erase that. What I'll do is I'll put a line through it. Okay, so that's wrong. Now, this is how we're going to fix it. Just copy this, maybe if I can, oh, no, one more. So we need to name this alphabetically. Now, since we do not alphabetize under the D, because that's not actually its real name, that means ethyl comes first. So I'm going to take this 5-ethyl, I'm going to cut it out, and I'm going to paste it there. So it's going to be 5-ethyl, and I can erase this hyphen as well. So it'll be 5-ethyl since ethyl comes before, so since E comes before M. So 5-ethyl, 7, and on the 7th carbon we have this complex branch. Now that is written in parentheses, right? So off the 7th carbon we have this thing. So the 7th carbon on the 1st and 2nd carbon of that branch we have a dimethyl, 2 dimethyl groups, or 2 methyl groups, and the main branch is a pentyl. And we can say, so this is 5-ethyl, 7,1,2-dimethyl-pentyl tridecane. There we go. So that's a complex branch. You won't get many of those, and we will practice them. It is in your homework, rather your home fun. So we can continue then. And this is another good example. So here we have an example where we're competing for the numbering of a chain. So what I mean by that is we can start here at the 1. This is the correct version, but we could also, instead of going from right to left, we have 7 carbons. We could go 1, 2, 3, 4, 5, 6, 7 carbons. So both seem right. Going up and going from right to left will give you the same number of carbons and therefore the same parent backbone. But we have to choose which one is correct. And the one that's correct is the one with the most number of side chains and the simplest one. Because if we went up, we would actually end up giving ourselves a lot more work. If we went up, we would have a complex branch situation here. And you saw how messy that can get. So we're not going to do that. We want to choose the simplest one and also the one with the most substituents. So we begin at 2, 3, 5. We have 3 methyl groups. So we can say 2, 3, 5 trimethyl. And again, we're naming using the methyl, not the tri. So 2, 3, 5 trimethyl. On the 4th carbon, we have a propyl group. I haven't seen that, I don't think. That's just the alkyl group that has 3 carbons. So that's 1, 2, 3. So off of the 4th carbon, we have a propyl, and that exists off of a large parent backbone heptane. Now, I did say we weren't going to talk too much about the reactivity of alkanes. We have a whole other day to do that. But alkanes are generally pretty stable, of course, unless you ignite them. So um, in those situations, of course, they are not. But of the organic compounds, because your sp3 bond hybridizations are fully saturated, uh, it's the only type of reaction that can easily be accomplished is combustion. But we'll talk more about that as we go along. And this last part here should make sense, especially given that what we just finished talking about in the last unit. So the longer the carbon chain, the more solid it becomes. So it goes from ethane or methane, ethane, all gases, propane, a gas, and slowly start to become more and more liquid, and more viscous, all because of intermolecular forces, but that we covered in the previous unit. So your home fun is an alkane worksheet that I have already posted. It's in our class website. It's in our second unit, which was empty until now. So here's this lesson in the form of a PDF file. And under Home Fun, I posted the naming alkanes worksheet. We will definitely go over this when I come back. There was a lot said. Please feel free to pause. If you need to pause this 20 times to get through it, that's fine. It does take practice. It does take listening to this. So it's worth, I think, recording this so that you can have it and you can listen to it on your own time and pause as you see fit. You do definitely need to practice this in order to get the naming correct. So we're going to go over all of this again. Plus, we'll take up this worksheet. So hopefully you're not too anxious, and hopefully this helps. I'll see you in class.